Hi everyone. So in this discussion, for this discussion post, I decided to go over reduction of order, which was a technique for solving homogeneous differential equations that I've had a bit of trouble with over the past week and on quiz 3, so I thought I'd try and review it and possibly refine my understanding of it. And so I decided to do exercise 2.1.8 from one of our textbooks, which is right here. So we're given that y1 is a solution to this second order homogeneous differential equation, and we have to show or prove that y2, that a second linearly independent solution is given by multiplying the first times this gnarly integral here that we'll have to evaluate in a second. But so I've rewritten this theorem, this question as a theorem, which basically says that if omega is the domain of the differential equation, a subset of the real line, and we're given that y1 is a solution, then y2 is again given by y1 times this gnarly integral. So in order to prove this, we have to show that y1 and y2 are linearly independent on omega, and we also have an additional requirement, at least in this case, that the term, the polynomial coefficient in front of the second order term, cannot be 0. So if it were 0, then the second order term would disappear and well, it'd become the first order differential equation, but we want to evaluate the second order differential equation. And further, by putting the equation in standard form as it's written here, we're dividing by a naught. So if a naught is equal to 0 at any point on the real line, then we simply exclude those points. They are singular. So moving on to the proof, we make the assumption that y2 is twice differentiable. I'll talk more about that in a second. But this notation just basically means that y2 has two continuous derivatives on omega, on the set omega. And taking the first derivative, we have a product rule for y2, which would just be first times derivative of the second plus second times derivative of the first, as I've written here, which simplifies to this term. And then the second derivative, for the second derivative, in these first two steps, I tried to emphasize the fact that the differential operator, as we are considering it, as is a linear operator. So the sum of the derivatives is equal to the derivative of the sum. And in this step, I wanted to also emphasize the concept of the derivative of an exponential with a function in the exponent is the natural log of the base times the derivative of the exponent times the original exponential function. And we all know that ln of e is just 1. And these two terms cancel, which gives us this term. Now we substitute this derivative and this derivative into the original differential equation. And after distributing the p of x through the first derivative, we see that these integrals, which I've colored blue, can be pulled out of those terms, the p of x just being moved over next to this term, as in this step, and we get the differential equation back. So we know this differential equation is equal to 0 because y1 is a solution of it. So this integral and this term disappear, they vanish, and we're left with the first and second terms. And since the derivative of an antiderivative is just the integrand, we have the negative integrand here, which is negative p of x plus p of x is 0, because the other terms are the same. So we know that y2 indeed satisfies the differential equation on omega. Now our task is to show that y2 and y1 are in fact linearly independent, and we can do that with this tool called the Wronskian. So by throwing our functions in there and their derivatives, their first derivatives, which we solved for earlier, we And by taking the determinant, we see that the two terms here at the end cancel, and we're left with an exponential, which is never zero, at least for real numbers. So they are indeed linearly independent. And therefore, this y2 is a solution to the differential equation in addition to y1. Now, as I said earlier, I wanted to remark on the assumption that y2 has two continuous derivatives on omega, because most of the functions that we have yet seen are in fact C infinity functions, so they're analytic at most of the points in their domain, like the sine, cosine, exponential, logarithm functions. Of course, there's other ones that we haven't yet seen, but anything, well, say functions like tan of x or any of the trig functions, they are C infinity functions. Like, for instance, tan of x, the derivative is secant squared of x, and we can continue taking derivatives, and so it is a C infinity function. Although we haven't seen the series for tan of x, it is indeed a C infinity function. Now we move on to an exercise. I wanted to go through another problem just to kind of nail down the reduction of order process. And so this is 2.1.9, so we're given this differential equation and y equals x as a solution, which we have to verify. And we have to use reduction of order again to find the second linearly independent solution, and then write down the general solution to this differential equation. So this equation is not in standard form as it's given, so we divide by 1 minus x squared, all of the terms, and we get the standard form of the differential equation, and we see that this term here, p of x, has singularities at -1, x equals -1, and 1, where the polynomial in the bottom is equal to 0. So we exclude those points from the domain. And the same thing happens for the q of x. So those 2 points, we do not include them. So it's just a real line minus these 2 points. We're using an interval notation with the cups to unify the intervals. We have the domain of the solution. And I did want to mention that Wolfram's Math World has an excellent page on all the different types of singularities we might come across. So we've studied ordinary points and singular points, which I mentioned. And so our first task was to show that y1 equals x is a solution to the differential equation. And so by taking the first and second derivatives, which are just 1 and 0, we substitute this back into the dE and get 0. So now that we know y1 is a solution, we must we must find a second linearly independent solution. So we make the assumption that y2 is equal to a function of x times our first solution, which means that they're linearly independent, and which equals to u of x times x. And then we take the first and second derivatives, the first being a product rule, first times derivative of the second, which is just u of x times 1, plus second times derivative of the first. And then we do yet another product rule, and we simplify to this term. Now we substitute back into the differential equation again, and we notice that these two terms here, this product, and when we distribute this through, we have u of x times x over x squared minus 1. If we take a negative out of the denominator in this term, we get x squared minus 1, so it's negative u of x times x over x squared minus 1 plus u of x over x squared minus 1, which is just 0. So those two terms vanish, and then we are left, after a bit of simplification, with this term here. And this is where the reduction of order process begins. So we substitute a capital Greek letter psi equals to u prime, which means that psi prime is equal to u double prime with this change of variables, to obtain this first order differential equation, which we have seen before. or at least we've seen this general form before is what I mean. And so we want this left-hand side to look like a product rule. So we solve for an integrating factor, mu of x, which equals to the, as we saw, exponential of this p of x term. And we know by properties of exponents that e to the sum of two terms is equal to the product of the exponentials, as long as they have the same base. So the exponential of this antiderivative plus this antiderivative is equal to the exponential of this antiderivative times the exponential of this antiderivative, just to simplify things further. And a note on notation, this exp is just to bring the exponent down so that it's like an inline equation, and so the integral isn't kind of scrunched up there in the exponent. It just makes everything a bit clearer. And so the antiderivative of 2 over x is the natural log of x squared, and the antiderivative of x over x squared minus 1 is just 1/2 natural log x squared minus 1. And I suppose I should have included absolute values symbols here, the brackets, the bars. But if we are considering a domain that is only positive, then I suppose we wouldn't need them. Yes, so I suppose I could have put bars there, but... And then, since we have our integration factor, our integrating factor, we multiply this by every term, and I'll leave you to verify that this is in fact the derivative of this guy, of our integration factor. And we put the original term into our differential and integrate that. So it's a lot like a Riemann-Stieltjes integral, where we're integrating 1 with respect to some function, and we just get the function back. It's like traversing the function f of x equals to 1 at the rate of some function. And I looked this up yesterday because I kept hearing it in the lectures and I hadn't really given it much thought, but the antiderivative of 0 is in fact not 0, so it is a constant. So if we were to put this 0 into the differential, as we put this function into the differential, it would go in as c, and the antiderivative of dc is in fact c. So we solve for psi by dividing everything by this x squared x squared minus 1 term, and we now have psi in terms of x. So we resubstitute for u prime of x, and then we find the antiderivative again. So pulling the c out because it's a linear operator, and pulling the constant of integration out as well, so we can just worry about this integral. We see that it is a trig integral that we probably came across in Calc 2. And I did start writing up a page that generalizes this integral, because integrals are fun, let's face it. So I'm working through a reduction of order proof for or identity for this integral, and so when it's up, I'll post a link to it. I believe Wolfram Alpha gives a solution in terms of a hypergeometric function, a Gauss hypergeometric function, and I'll try to see. I'll try and obtain this result for myself. So for the trig integral, we notice this x squared minus 1 in the radicand, and because this identity, by subtracting 1 from both sides, we get a secant squared of theta minus 1 equals to tan squared of theta, will probably simplify this integral quite a bit. So I gave that a try, and by letting x equal to secant of theta, we substitute that in for all the x's, and if this integral here, if you think about it, we're integrating with respect to secant of theta, so it's a lot like integrating with respect to x. We just treat these secant of theta as kind of like our variable of integration in a sense, although it's not really. But we can take this secant of theta out of the differential, as by taking the derivative of it. So we have secant of theta tan theta times d theta divided by the secant squared theta times tan squared of theta, because secant squared theta minus 1 again is equal to tan squared of theta. So that's how we get rid of that square root. And by canceling the secant with the secant in the numerator, and these two tans cancel, so we have the antiderivative of 1 over cos of theta, which is just the antiderivative of cos of theta d theta. So this integral reduces quite a bit to a very, very simple integral that we've seen before. So this just equals to sine of theta, and again, remember I took the constant of integration out already, so we're just going to concern ourselves with the integral. And now we need to convert this function back to a function in terms of x, because we made this substitution x equals to secant theta. So if secant theta in a triangle is equal to the hypotenuse over the adjacent side, here it would be equal to x over 1. So the hypotenuse is of length x and the adjacent side is of length 1, which means that the opposite side of the triangle by the Pythagorean theorem is equal to the square root of x squared minus 1, which means that sine of theta, which is equal to the opposite side over the hypotenuse, is equal to this opposite side length over x, which we know to be the hypotenuse, which gives us this solution with these two constants. So since we know what our function u of x is, we recall that y2 of x is equal to u of x times y1 of x, which was just x, and we know y1 is a solution. We multiply x times u of x, and we obtain this term. So the general solution, or the homogeneous solution to this differential equation, is as I've written it here, because k of x, k times x, and so we have kx times the other solution, and we know that by one of the theorems in the textbook that linear combinations of our solutions are in fact also solutions. I believe this was the superposition theorem. So this kx and y1 of x. So first off, the homogeneous solution is going to be y1 of x, constant multiples of y1 of x and y2 of x. So y1 of x we knew to be a solution is equal to x, constant multiples of x, so we just combine y1 and this term that arose while we were solving for the second. So it's c naught of x plus c1 times square root x squared minus 1, since these two terms are combined as c of x, c times x.